Okay, so this is a summary of the different bifurcations that that occur in the discrete systems. This is what we saw. We saw it really fast because we did it the first time. We saw saddle node, pitchfork, transcritical. I'm not going to show you, but it's the same thing before. And that's what happens when this derivative becomes greater than 1 by actually becoming greater than 1. It's not negative. It doesn't become less than minus 1. It can also leave. We saw that before in. Excuse me. You can also have departure in complex conjugate pair, and we're not going to look at that, at least not this time. And we might, I'll take a poll later on what I should give later classes on. Now we're going to look at what happens when it exits by -1, and that's a whole other field. You might think it's just the same thing, but it's going to be quite different. And that's called the period doubling bifurcation, and it's impossible for continuous dynamical systems for the reason that I said before, because you can't jump. If you were continuous, you couldn't say I go from right to left, I go from right to left, I go positive, I go negative, without in between going through 0, whereas in a discrete one you could. And we will illustrate it via the logistic map, which is this. This is a quadratic map, very simple. And you can look at it in the following way. The xn plus 1 is being multiplied by something, which is, suppose that xn were small compared to 1, then it would be xn plus 1 is a xn. You're controlled by a. If xn is, it's just like shrinking and growing depending on the size of a. Okay, if xn is small, right? It's just those linear maps we were looking at the first time here. If xn is small, it's like this. If xn is large, then this plays a role, and this damps the possible growth. And this was the first model for population. Population dynamics was the first, I guess, application for discrete dynamical systems. Its origin is very old, but it was popularized in the 1970s by people like Robert May and became very famous in the 1970s when it was studied by Feigenbaum and by Coulier and Tresser. And how many of you have heard of this period doubling, Feigenbaum and Tresser? Who you have and who has not? Okay, so maybe the demonstration's going to work, or maybe not. I will see. It didn't look very promising before, but let's see. No, why do I have because I think I told you these. I always meant to write my own, but I kept using it, and now it's.
Try Safari.
I am in Safari. I am in Safari. I can't do it at all on Chrome.
Okay. So.
You think I should
restart
yeah.
it?
All right, but okay.
It's a what do you call it?
Applet, Java.
Yeah, it's
yeah,
Java.
It's Java problem. That's right. I know. And for a while, it worked on one version of Java, but not the more recent ones. So I had to keep telling it, do not update Java. But eventually, when I let's try it again. Okay, we'll try that again. Do. Okay, good. Okay, so I'm going to take this value down, this value here. I'm going to take it to 0.5. Reset, and I'm going to say step. Okay, you see it doing the cobweb picture, right? We started off with initial value 0.35 that was here. We went to the function that was here. We went, okay, oh, yeah, this is the opposite convention than the one I've used. The red is the black here is the diagonal, the red is the function. But you might never notice that if I hadn't told you, but I'm telling you. Okay, so we went from black to red, we went vertically, and then horizontally, and then vertically. Anyway, you can see it's converging to this single fixed point. There's one fixed point here that's the intersection of the curve with the diagonal. And now I'm going to increase A, and that's still pretty much the case, I guess. Yeah, I'm just going to go down like that. And now I'm going to make A 1. And I think you see, do you see that there are 2 fixed points now? Yes, you see this one here? Maybe I'll make it a little bit higher. Yeah, so you see 2 fixed points, one here and one here. And let's start. And you may not, okay, let's start from some other value. Let's start from 0.7. Clear. Stop. Start. Wait, where did I start here? Reset. There. Okay. Anyway, go straight there. If I start from 0.1, say, it's going to go here. So it's not because it was closer to this one that it went this way. And I think you'll see this from what we just discussed. The slope of the function is less than 1 over here, and the slope of the function here is greater than 1. You can see it's greater than 1. It's above the diagonal. This one has become unstable. This one is stable. We now have 2 fixed points, one stable and one unstable. And so we'll study what the different, I mean, you know the scenarios by which this can come about. We'll discuss them in a moment. Let me try and make you perhaps a little more curious. Let's increase these values. No, start here. Okay. Okay. Okay, you notice what's happening now. Do you notice that the fixed point, you notice that they're spiraling in? Do you see that little tiny spiral? Okay, and of course you remember that that has to do with the fact that the fixed point now has a slope that's negative. So it's going like that. Now let's increase this further. Okay, it's again spiraling in. You see the spiraling is closer, excuse me, it's slower. You have time to see a bunch of the different different backs and forths. Let's make it it's not doing the same thing. It's unstable, right? Okay, and now I'm going to, okay, but we don't see it moving, and yet it is moving. I mean, I'm telling you that because you can see that the only button, sociological proof, or the only button I can click here is stop, from which you can see that it's continuing, but it's not moving. So what's going on? Let us clear it. No, let's stop it, and then let's clear it. And that tells us to use as initial condition what the last one was. And let's start. And what's it doing? It's going around a box. Now, is it really going around a box? No, it's going from right to left, right to left, right to left. Remember, it's this, what I said you couldn't do with continuous time. How could you're not going in between. You're not passing the fixed point. You're going to the right, to the left, to the right, to the left. So the whole iteration looks like this. Go up here, go here, go here, go here, go here. And that is an exact, it's not a fixed point anymore. It's called a 2 cycle. And this is something that's not possible. This transition that we just saw is not possible in a continuous time dynamic system. So let's just go back to the class and discuss how that comes about. So we have the logistic map here, x of n plus 1 equals f of xn. We have the simple quadratic form. What are the fixed points? Well, we're looking for when this map leaves leaves x unchanged, so we can have either x equals 0, x bar equals 0. We saw that. We saw that there was always a fixed point at the bottom at 0. And there's another possibility, which is x is, excuse me, which is 1 is a times 1 minus x, right? We just divide through by x bar. And so we get a simple formula for x bar, which is 1 minus 1 over a. You saw as I increased the a that we got this new fixed point. Okay. You can see for a sufficiently, you need a to be greater than, when you to get this new fixed point, you need x, you need a to be greater than 1, because otherwise this brings you to the negative values, and we're there's nothing fundamental about this, but we're restricting the domain to be x positive. For example, in population biology, x is only positive. So we need x bar not only to be real, as we usually do, but also to be positive, and so you need a to be greater than 1. If a is too small, then this thing is too big, and you are subtracting something which is bigger than 1 from 1 and get something negative. Okay, yes?
Just curious, what's the physical meaning of this A? For example, what if it's in population? What is A?
It's the reproduction rate. How many baby rabbits each rabbit has.
Regarding the point you made that in continuous dynamical system, this box thing is
Yes.
not possible.
Yes.
Okay. I was just curious to know, like, so if we consider any physical dynamical system,
Yes.
which is indeed continuous,
Yes.
but because of our limitation
Yes.
in measurements,
Yes. No.
we
No.
have just discrete data.
Yeah, but no, that's not. No. The right way to look at it. I mean, I think you'll tell me if I'm answering your question, because you said so often the speaker does not answer the question. Indeed, I share your feeling that physical systems are all continuous, so we want to see it, how this happens continuously. And the main way that this happens continuously is that you have already had a Hopf bifurcation, you have a limit cycle, and what you do is the way you study it is you make you pierce it with a plane, and so you're hitting, so the map is from each point on the plane to the next plane where the limit cycle hits. Okay, and so there isn't an idea of taking the delta t smaller and smaller. This limit cycle, it has a period. You're looking every year at what the sun is doing. You're looking at every rabbit generation in the spring. It doesn't make any sense to consider I mean, you can look at it, but it becomes a different problem. You're looking. There's an actual physically significant or phenomenologically significant meaning to sampling every time, which is not just you've chosen delta t to be 0.01, and so we're going to look at it every 0.01. Does that answer your question? No, you want to try and ask it until I understand it?
Yeah, I mean, my point was like, so suppose we are trying to make interpretations for a physical dynamical system, for
The
which
continuous
for
one.
a continuous physical
Yes.
dynamical system, but we have just a discrete data.
Yes.
So can we conclude while making inference that this thing, this box thing is not possible, because though the
Yes.
data is discrete, but the system is governed by continuous
no,
dynamics?
we cannot. And we cannot. And indeed, I don't know. Have you studied numerical analysis? You know about different schemes for integrating differential equations.
Yeah, I have
You know
some
about.
idea.
Okay, this when you discretize an ordinary differential equation, you turn it into a discrete system, which can then do things that the continuous one could not.
Okay. Yeah.
Bad things, and that is what numerical instability is.
Yeah.
It's a property that's not shared by the continuous one. Eventually, if you get your delta t down enough, you will get rid of those other bifurcations. But that's right, you cannot. So I guess in a way, but now I think the answer to your question is yes. I mean, if we recall what your question was. Your question was, if we have gotten our discrete dynamical system by time discretizing
Exactly.
a continuous one, can we conclude that certain things can, and yes, that is right, the different kinds of numerical instability that we get from time discretizing a differential equation are not properties of the differential equation, and we can conclude, oh, there's something wrong with my code because this is not what's supposed to happen in my continuous system. So the short answer was yes. Right. Okay. Yeah, that's a good question. More good questions? Bad questions?
Maybe an add-on point to this. So when you talked about the numerical, numerical error,
Yes.
so it's like when we are trying to approximate the dynamical system by discretization and trying to get an evaluation of the system.
Yes.
Now, if I talk about experimental part, where the system is actually a continuous dynamical system, but we are just
Yes.
able to get
Yes.
a discretized data
Yes.
of
Yes.
the actual phenomena.
Yes.
So
Ah,
even
no, then that won't happen because the system knows it's a differential equation. These are samples from
Yeah,
a
exactly.
continuous one. With the numerical one, it's different because you're controlling it. You're making it do
Exactly.
so. Yes, that's right. Yes, there's a big difference between sampling from something that is continuous to actually making it. Okay. When you sample from something that is continuous, it has all the information from the time
yes,
that's going on. It has all those intermediate values to do that. When it has a time, when you go to time 10, it had to go through, the system had to go through time all the times up to
Yeah.
10. Whereas here, it only used the information at the samples. It knew nothing about what was happening in between. If you sampled every 1, 2, 3, it based the answer at 2 just on what happened at 1. It didn't use the intermediate information, and here the system did. So I see we are on the same wavelength. That's good.
I'm an experimentalist, so
Yes,
those
yes,
things
yes,
I
yes,
don't
yes.
understand.
But you don't have to be, that point, say, you don't have to be an experimentalist to have that point. People who are numericists, they are trying to approximate differential equations. And when they approximate them by discretizing time, indeed, you want to know what you're doing. So all these are, this is exactly the right kind of question. Okay. So returning to the but are there more questions? No. Returning to the,
Just
yes.
a quick one then. So on the previous slide, when you said period doubling is impossible for continuous dynamic systems, but is it more appropriate to say that it's just not, we cannot just detect it for continuous systems?
No,
It only
it
exists
cannot happen.
entirely.
It cannot happen. It cannot happen because well, essentially, what is it I'm trying to say? Well, if I start to say it, it's not going to work out. Here I want to make the complex plane, and I want to say that we are when there's a bifurcation, this is the complex plane with the real and the imaginary part, and I want to say that the eigenvalues are crossing here. Here I talk about the unit circle. I say I'm not sure this is all going to work out, and mostly what we mean by this unit circle is the exponential of these. You know that when you take the exponential of the imaginary axis, you get the unit circle. But to get to -1, I'm going to claim, now I know you're going to say that you can just take pi. I'm sure you're going to get the right answer to this. That's going to save me. You do e to the I pi, of course, is -1, but you're supposed to measure this in frequencies, and the frequency will be too small, and you'll never get there, and you're mapping this there. Yes, please, can you help me out?
So, well, one thing I think about this is, if it were a continuous system,
Yes,
that would, to me, and I've just seen such a picture yesterday, so that's why I'm thinking.
yes, yes,
You start off with a limit cycle.
Yes.
And it splits.
yes.
So is that's not exactly, it's like period.
Oh, no, that splits, you mean into two different ones, or one?
It goes from
Oh, that's not,
one
no.
closed loop into a loop that doubles back on
That
itself.
is a period doubling bifurcation. That's
It
that's
But
the
that's a
canonical
continuous-
example.
That's a continuous
It
system.
is, but what is, it is indeed, but what is, okay, it's a period doubling bifurcation of the map, of the Poincare map, which is the one that I did by of the Poincare map.
Yes.
A period doubling bifurcation would be the, I mean, you're taking out a dimension there. That's a one-dimensional system on the on this Poincare map.
Okay.
Yeah,
okay. Yep.
So possibly it's just a question of words, what we're saying, because yes, the continuous system, it does go through a
So in
period
state
doubling
space, you
bifurcation.
would not do this. In the entire state space.
Yes,
it
that's
would
right.
do it.
You would not have a fixed
Okay.
point. Yeah, that's right. It's a limit cycle that does this. You would not have a fixed point that's standing here, being a fixed point of a dynamic system, an X bar, that suddenly says, oh no, I'm going to go 2, 2, 2, 2, 2, 2. It can't do that because it has to do continuous time. So it can't go here and then change its mind and come back. It's going to have to pass through 0 and yeah, the right, yeah, I maybe I can think about it better, but that's exactly a continuous system goes through period doubling. When you map that continuous system, when you have a limit cycle in a continuous system and you map that to a map, which is the called the Poincare map, which is piercing a plane and going from one piercing to the next piercing to the next piercing. And that means that, as we were talking about with the abandonment of everything in between, it's a map on that plane and you're not paying attention to what happens over there. It can jump. It used to do this, and now it's going to jump here and here. But the jumping, it's not doing continuously. It's not doing by walking over on that piercing plane going here. It has the whole limits. It has the whole cycle to go and decide that it wants to be here, and then the cycle to decide that it wants to be here, and then the cycle to decide that it wants to be here. It's not walking on the plane here and here. It has something in between. The way the rabbits have that whole generation in between that you're not seeing. Unlike the time discretization that you were talking about, where you can take the delta t smaller and smaller, and you better get reasonable results there. So, still, perhaps leaves something to think about. Okay, more questions? Okay. They don't even have to be as good as the questions that you all asked already. They could be less good questions. They could be, what does A mean? Or, okay. We saw that in this logistic map, we go from having a fixed point at 0 to having two fixed points, one at 0, one at A, excuse me, one at 1 minus 1 over A. That's not strictly true because, of course, we had the negative one before. It's a transcritical bifurcation, so we used to have 2 points, and now we have 2 points after A hits the value of 1, but we're just not counting it. You know, it's impossible to go from 1 to 2 fixed points. We know that from topology from the first class. We have to go from 0 to 2, or from 1 to 3, or something like that. Indeed, we went from 2 to 2, but we're not counting that one because it was negative 1. So it creates the other fixed point is a transcritical bifurcation, and we can do all the calculations that go with that. We look for the, we have our right-hand side of the logistic map that looks like this. The derivative, of course, is A times 1 minus 2x, because we have an x squared over here. The 0 point, its derivative is A, so you can see that it is less than 1 for A less than 1 and bigger than 1 for A bigger than 1. When you take the derivative of the, evaluate the derivative at the new point, you get minus A plus 2. And now, okay, here's important thing that people always, okay, I've been giving this class a long time, I give exams, people always get this wrong. So anyone who, I mean, of course, you're not all taking the exam, but everybody, pay attention here. We're interested here in when f prime of 1 minus 1a becomes greater than 1 in absolute value. We're talking in one dimension. Even in one dimension, there are two ways you can do that. One is one is becoming greater than 1, and the other one is becoming less than minus 1. And people always forget that second thing, you know, like high schoolers. The absolute value, there's two possibilities on the right and on the left, right? Don't be like the secondary schoolers. You have the two possibilities here. So let us see. Okay, and what are we doing? We're looking for the interval of stability of this new point. This new point, the one that we saw when the parabola, when we raised the parabola, we created a new point. Okay, so we look at those two things. we recall the derivative, meaning what controls the stability of that new point, 1 minus 1 over a, is minus a plus 2. Okay, so let's do algebra on it. Let's multiply through by minus 1. And in doing that, kept track of what I was doing with the colors, right? That's to say this minus 1 became this 1 here. And you'll see why I did that. Everybody agree with what I did? It's just, okay. And then I added 2. So I find that the interval of stability is between 1 and 3. And the 1 came from this 1 here. And the 3 came from the minus 1, the one that I told you to be careful of, right? Okay, this 1, this one here, the a greater than, is not surprising. This is the point at which the new solution occurs. So this is the transcritical bifurcation. We know that at a bifurcation, there's simultaneously a change in stability and creation of a new solution. That's what happens in the pitchfork bifurcation, the saddle node. That's always what happens. Here, because the solution is barely unstable, it's marginal. This is where it changes sign, right over here. Okay, so that's not surprising. That goes with creation. But what is this other thing? What is this 3 here that came from the minus 1? That's the one I told you to keep track of. When you're looking for absolute value being less than 1, you also have the minus 1, and keep track of it. So what is that 3? Well, I gave up some of the suspense by showing you the demonstration before. Let's look at, this is in case I don't have a demo. Here it is. We're increasing the a, we're raising the parabola, and here, as the derivative is now going to be negative, and so we know that we have this alternating behavior, and it's going to become so negative that the slope is less than minus 1, and that is what's happening here. The slope is less than minus 1. And where does that happen? We just calculated it. It happens at a equal 3. And that is when you get that square. That original fixed point has become unstable in favor. Okay, now we said a square, but we really shouldn't be saying a square. That's because we're drawing it in 2D. We should say it's a pair. The fact that that's just our graphical construction. We would draw x and f, but it's going from x, this x to that x to this x. It's a 2 cycle. It looks like a square when we include the axis there. Okay, and that is indeed that's the point of the location of the period doubling bifurcation is a equal 3. And let's see if we can get back that demo. See, do it. Maybe. Yes. Okay. So I was at 3.1. Remember, I sort of knew it was going to happen. This is what we had. Let's go back to let's go to 2.9. And there, now 2.9 is converging into the fixed point. Okay, and after we cross 3, at 3 you couldn't see it. It would be just marginal there. And 3.1, well, we saw what it did. And now it stops. It stops because you don't see any more motion, and yet it's continuing on. It's continuing to iterate. It's just not changing. And we see that by clearing the initial condition. We stop, we clear, we start from where we were. Oh, no, that's not what I did. Come on. Now we stop, we clear, we don't reset, and we start. And now it just goes. Okay, let me now spoil further suspense. Let's see what happens here. Okay, let me stop, let me clear, and let me start. Okay, I still have a 2 cycle. Stop, let me do 3.3, let me reset. Oh, I didn't mean to do that. Oh well, let me start. Okay, now let me stop, let me clear, let me start. Okay, we still have 1. Let me stop, and I do 3.4. reset, start,